Okay, I make it 5 past, and it doesn't seem like there's anyone else joining, so let's get started with today's course. So thank you everyone for coming to today's Introduction to LAMMPS. This is going to be an ARCHER2 course. Hopefully, those of you who are wanting to follow the course and do the exercises have already applied for an ARCHER2 account. If not, we'll be doing a session to provide you access and to make sure that everyone's been able to log in. My name is Julian. I'll be one of the 2 instructors for today. The other instructor, Rui, is here. Rui, do you want to say hi? Rui is being rather shy. Ah, there we go.
No, I'm here. Camera was taking a while to turn on. I don't know why.
Yeah, and yeah, the 2 of us will be talking through an introduction to LAMMPS for today. Everything that we will be saying is available as part of the course material. You can find the course material by going in the, you can find the course material by following the links on the ARCHER2 course page. If you go down a bit, let me know, by the way, if you'd like me to zoom in a bit more, or whether you're able to see what's on the screen properly. But yeah, if you scroll down a bit, you'll see there's the course material and there's the course chat. The course material is a carpentry style course. We quite like these carpentry style courses because it means that you're able to follow along and go a bit faster if you need to, a bit slower if you need to. I've put the link to that in the chat as well. And finally, there is a course Etherpad and a link to that. Now, throughout this course, the aim of this course really is to help you get as much as you can from Rui and my experience of using LAMMPS. So please do ask questions. These courses are only good when you're asking questions, and we will be asking a number of questions in order to try to aim the course and talk about the subjects that are of most interest to you, where possible. You can either ask questions by putting your hand up. When I notice that anyone's put their hand up, I will ask them if they want to speak. Be aware that if you are talking, the session is recorded, so your question will be recorded, but that's, that should be fine. If that's at all a problem for you, let us know and we can remove that. Alternatively, you can post a question in the Collaborate chat, which is here. And anyone can post a question there, and either Rui, either the person who isn't teaching at the time will answer in chat, or will ask the question out loud on your behalf. And then finally, you can ask. We will be checking and doing some of the exercises actually on the Etherpad. So by all means, feel free to use the Etherpad here to ask questions. So you can always, with the Etherpad, you can add your name if you want to. You can change the color that you're using. I quite like that color. So there we go. Ooh, that's a bit too dark, actually. Let's make that a little bit lighter. There we go. Yeah, so Etherpad is another place that you can ask questions. Cool. So today is going to be a rather somewhat intensive course for LAMMPS. We've aimed this as an introductory course for people who have either never run LAMMPS before or have maybe run it once or twice and want to see what else it can do other than the very, very basic, oh, here's a Lennard-Jones fluid, here's the colloids example that the LAMMPS manual always says we should use. And we've kind of split the day into 2 parts. In the morning, it really is more a case of looking at how do you get a job running, like going from 0 to getting something to run, how quickly can we do that? We'll also talk about getting you set up on ARCHER2, and we'll show you a bit about how to run LAMMPS on ARCHER2, because at the end of the day, this is still an ARCHER2 course. And after that, we will move into slightly more advanced techniques. So things like how can you improve your, how can you read a LAMMPS log file? What can you get out of a LAMMPS log file? How can you improve your simulation efficiency by checking out the LAMMPS log file? Also some advanced inputs, and we'll talk a bit about additional software that are available as well. We will try as much as possible to stick to these timings. Yeah, so I mean, feel free to follow along, feel free to ask questions, and yeah, do take part. Like, the aim really is to help you as much as possible. So I've kind of described the course structure and methods. So let's go straight into introductions. It would be really, really good and helpful for Rui and me if we could get an idea of basically who you are and what you're hoping to get from LAMMPS. So if you could, in the course Etherpad, let us know your name, maybe not necessarily your place of work, but like what it is you're working on, whether this is your first time using ARCHER2, whether this is your first time using LAMMPS, and why you're interested in learning how to use LAMMPS, maybe even what sort of systems you're interested in. So I'll get started. So hello, my name is Julian. Work at BPCC as part of the in-depth support team. So I've been using LAMMPS now since 2012. Okay, and I've used it on a number of simulations. So at first I was doing crystallization. And recently I've been doing more discrete element methods. Cool. One of the things with Etherpad is it's very easy to accidentally write on the same line as someone, but you all seem to be able to sort it out. Also, don't worry about writing on this. This is the one bit of the page that we'll, like this part of the course, we will remove from the final video. So, yeah. Cool. So, oh, cool. Polymer-based nanocomposites. I expect Rui's done things that are similar, not adjacent, but not exactly the same. Yeah, with surfactants and tribology, you'd imagine that there's a lot of overlap. Topological polymers, yep, that's definitely Rui's field. Fluid dynamics. I'm guessing this. I'd be interested in finding out which level of fluid dynamics. Liquid-liquid interface.
I've also done some of that liquid-liquid interface, water and oil.
Cool. And HPC from Kevin. Oh, cool. Yeah, GROMACS, but interested in LAMMPS for DPD and MDPD, and coarse grain simulations. Cool. Excellent. Great. Well, thanks everyone for writing this. I will put in a couple of spaces just so that this is a bit hidden. It'll catch up. Cool. Could I ask very quickly, please could you put your hands up if you have already managed to log into ARCHER2? So if you go on the collaborate session, at the bottom there is a little person with their hand up. If you just click that, that'll help us. That'll help me get some indication of how many people have already managed to log into ARCHER2 or not. So 3 people. So about half of us have managed to make it to ARCHER2. I mean, definitely. Yeah. Okay, cool. That's also quite helpful for me to know how much we should spend on the next session. One important thing about these courses is we very much value feedback. As I said, we want this course to be as useful for you as possible. So let us know if there's something you want us to cover more deeply. Let us know if you feel we're going a bit too slowly. Let us know if you think we're going a bit too quickly. And also at the end of the course, you'll receive an email which is going to ask you for your feedback for the course and what you thought of the course, what you thought could be improved, that sort of thing. This is the first time that we're running this particular version of the course. We used to run it as an online course with slides, which wasn't as good in my opinion, but let us know, like, it would be really helpful for us to know what we're doing well, what we're doing poorly, what we could improve on, in order to make sure that the next time we run this course, it'll be a better course. So please do fill out that survey when you get it. Cool. So connecting to ARCHER2, I'm going to lower everyone's, actually no, I'll leave the hands up. Could I ask for the 3 people who have not logged into ARCHER2, could you put your hand up if you have an ARCHER2 account already? So one of you has an ARCHER2 account. Okay, cool. I'll lower everyone's hands down. So to get an ARCHER2 account, the first thing you need to do is get a safe account. You can do this by going in at safe.epcc.ed.ac.uk. I've put the link in the description. And if you've never logged in before, you can request an account for it, and eventually, so you'll need to enter some details just so we know where you're coming from, why you're wanting to access ARCHER2. And once you have an account, you'll get on a page that looks a bit like this. Let me zoom in so that you can see. And if you want a login account for this course, if you've not done so already, you should go log into Safe, go to Login Accounts, and request login account. Here, you'll need to enter a project. The project for today is TA100. This is apparently the 100th training course that we're doing. You can click Next. You want access to ARCHER2. There's only one option, so you can just click Next. You should maybe look at the terms and conditions. They're pretty standard terms and conditions of, be polite, don't do anything that you shouldn't do on a shared facility, don't be annoying to other users, be considerate of other people, don't do anything particularly hateful, and things like that. Once you've read those and once you're happy with those, you can request a username. If the username is already taken, let's say this one is already taken, you click this, then when you request, it'll say username is already taken, so you need a different username. Make sure it's an individual username, and once you've done that, Ruby and I will get a little message to approve your account. I already have an account for ARCHER2. I have an account for this course for ARCHER2. And once you have your account, you can log in you'll be able to log in. Once you have your account and your account status, which you can check by going into login accounts, your TA100 account, and if you check status here, it says active. Once you have an account and it is active, you'll be able to log into ARCHER2. Yeah. So with that, to log into ARCHER2, you need 2 things. We operate a form of dual authentication. We require people to have a user account password and an SSH key. Now, I'm happy to talk you through how to create and upload an SSH key if that would be useful, but please let me know in the chat if that's something you'd like me to spend some time on. Otherwise, I'm perfectly happy to assume that you will be able to find out how to do this by looking at the ARCHER2 webpage on connecting to ARCHER2. I've put the information for connecting to ARCHER2 here, but the ARCHER2 documentations have a lot of information on how to access the system, how to run various software, these sorts of things. So would anyone like me to show how to generate an SSH key and how to upload it to safe, or is everyone happy? Or put another way, please put your hands up if you would like me to generate an SSH key and show you how to do that and upload that to safe if this is your very first time logging into ARCHER2. And conversely, please put your hand up if you would like me not to, if you feel you do not need me to show this, just to check that you're still here. Cool. There are a couple of people who are still here and who are saying that they do know how to search, and I think no one has said that they want help doing this. So fine. Let's carry on. Where's my terminal? Cool. So once you've got your ARCHER2 account, and once you've got your SSH passphrase, your SSH key, public part of your SSH key uploaded onto safe, then you can log into ARCHER2. The way you would do that is by running SSH -I, then the path to your SSH key. For me, it's .ssh/id RSA. Window is a wee bit small. Yeah, I can improve that a bit. Is that better? Yeah. Close that. Yeah, so SSH ID RSA, then your username, which in this case is TA100JS at login.archer2.ac.uk. Yeah. Now at this point, if this is your first time logging in, it'll first ask for your SSH key passphrase. I've already logged in today, so it's not asking me for that, but it'll first ask for your SSH key passphrase. Then it'll ask for your temporary password, and you can find your temporary password on safe. If you go on login accounts, the login account you're interested in, and then down here where it says view login account password, you can click on there to see a temporary password. If this is your first time logging in, it will ask for your temporary account password, and then it'll ask you to reset your password. And the way that the reset happens is you'll be asked for your temporary password again, then your new password, and then your new password again, just to confirm that you've not forgotten it. In this case, I've already logged in at least once, so I will enter my new password, and I'll try not to say what it is. If I remembered my password. It's always one of those little victories when I remember my password. And at this stage, we are logged into ARCHER2. So in terms of the course, I've briefly hinted at passwords and password policies, but actually when you're entering your new password into ARCHER2, you'll need to choose a password which follows the ARCHER2 password policy, which you can find by following the link in the course. And the policy is that your password, by default, your password needs to be a minimum of 18 characters long, but for every degree of complexity that you add, you decrease the minimum length by 2. So if you use lowercase characters, then you're decreasing the complexity by 2 to 16. If you're using uppercase, you're decreasing it by 2. If you're using upper and lowercase, then you're decreasing it by 4. If you're using numericals and punctuations, you're also decreasing it further. There are also certain rules, like we don't allow, the passwords must be different from one to the next whenever you change them. We don't allow more than 2 consecutive identical characters. There's a dictionary check that's done on every password to make sure that you don't. It's not easy to hack. Quite generally, the easiest passwords to use, the easiest passwords to remember, and the ones I usually use, is you sort of come up with a number of words that mean something to you and make a passphrase instead of a password. And that passphrase will have a high degree of entropy, will be very difficult to break, but will be easy to remember for you, which is kind of what you want from a password. So I'm seeing that someone's getting a permission denied. Give me a sec, I'll have a wee look to see. Could you let me know what your account name is, please? Like, what's your ARCHER2 account name? Mm-hmm. Cool. Let me check. Yep. Yep, that looks right. Cool. And could you let me know what error message you're getting? Cool. Okay, so that looks like you haven't generated, well, that looks like you're trying to point to an SSH key that doesn't exist. So when I logged into ARCHER2, I used SSH flag I to point to my SSH key. The reason I could do that is because my SSH key exists, it's there, and it's called IDRSA. You can see it here in the .ssh directory. If you've called your SSH key something else, then you'll need to use you'll need to point somewhere else with the -I flag right here. If you've not yet generated an SSH key and aren't sure how to do that, let me know, and I will probably talk you through how to do that in a private chat while Rui goes on with the rest of the course. Rui is taking over from the next episode. But yeah, I'll direct message you in a minute or two. The final thing that we'll briefly mention, though it won't actually be very useful for this course, but it might be of interest generally, is that you can transfer data from ARCHER2 or to ARCHER2 by using the SSH copy or rsync commands. And for both of those, you can find a lot more information in the ARCHER2 user manual, where we talk through things like how do you consider which data you should transfer? How can you ensure that you're transferring things as quickly as possible? And we also give examples and explanations of how you can transfer that, how you can transfer the data using these various things. But for this course, I don't think we'll be transferring any data, so this isn't something you should worry about too much. So on that note, it's time to move to the next chapter, where we'll actually be looking a bit more into LAMMPS, and I will help. I'm really sorry, I don't think I can pronounce your name. Is it Lakshmiranyana Reddy? I will help Lakshmiranyana.
It's just fine, ready. Ready.
It's just ready.
Yeah.
Okay, I can do ready.
Yes.
Brilliant. Sorry about butchering your name.
No problem.
But yeah, I will direct message you, and I will let Rui take over. This is Rui's first time teaching, so please be nice to him. And do you know how to share your screen, Rui?
Yeah, should be fine. Famous last words.
Cool. Then I'll stop sharing mine.
Okay, hopefully you can all see my screen. Yeah, so good. So I'm going to talk a little bit about the Archer architecture first before we delve deep into LAMMPS, because to know how to best utilize LAMMPS, you need to know a little bit about the underlying hardware system that we use and a little bit about the file systems especially. So ARCHER2 is a high-performance computing service. It is made up of AMD EPYC 7742 64-core CPUs. Each node has 2 of those CPUs, totaling 128 cores per node. And we have 5,276 nodes right now, totaling a maximum of almost 750,000 cores. So that's a lot of computing power, and for most purposes, nobody really needs that. But some specific applications will need a large proportion of that, or what you can do is you can run many simulations at the same time, or many jobs at the same time. ARCHER2 has different types of nodes for different functions. The first and the ones that you will interact with the most will be the login nodes. Those are the ones that your SSH terminal will connect to. That's where you upload or download your data to, and that's the only one that has access to the home file system. The home is where you should keep your data that the compute nodes don't need access to. So there will be maybe some transient data or some analysis scripts that you can run quickly, or some data that you use to generate submission jobs or something like that. You should not keep data that you want to run simulations on home, because the compute nodes will not have access to it. If you want the compute nodes to have access to the data, you should put it on the work file system. So that's the /work. The structure from then on is the same. It will be the name of the project. So in this case, /TA100, and then again, /TA100, and then there will be your username. So that will be your personal folder on both the home and the work systems that you can keep your data. You won't have access to any other projects with that account. You will have access to some shared folders on a project level directory, and there is some data there. So the yet-to-set files are there already. We'll show you how to access that a bit later. So the compute nodes have access not only to the work system, but recently a solid state system has been added. I believe it's been named Scratch or Temp, something like that, Julian. The purpose of that is for jobs that need very fast access to a lot of small files, so that it doesn't overload the regular work system. In ARCHER2, you can request anywhere from just 1 core for a job all the way to pretty much almost the entirety of the system. Obviously, that will come with budgetary constraints. But you should know that if you do not request the entire node, you will not have access to the entire memory of the node. So you'll have access to the proportion for the number of cores that you request. For some applications that require large numbers of memory, you might need to request an entire node, even if you don't need to use all the cores in a node, just because you need all the memory. There are 2 capacity memories, or there are nodes with 2 different memory capacities. The regular nodes, which are the vast majority, have 256 gigabytes, which is about 2 gigabytes per core. And the high memory nodes have the double that, so that will be about 4 gigabytes per core. You can see some stats here on all the more technical details of the interconnect bandwidth and the memory bandwidth. As you can see, anything that has to connect more than 2 nodes will have a bottleneck in terms of data transfer, as opposed to if it's in the same node. And also, maybe of note, is these non-uniform memory access regions. These have to do with the way that the AMD chips are built. This just means that each group of 16 cores has faster access to some part of the memory than the rest. So jobs that run over more than one NUMA region won't have these high memory bandwidth. It will be slightly low, but it can be helpful if your job can be broken apart into bits that don't need a lot of interconnection. So each NUMA region can then do a specific task, and if you can reduce your connectivity requirements that way, your performance might be vastly improved. So then, any questions about that? Anything that was not clear? Maybe show of hands if anyone has any questions. Okay, well, then let's step into how to load LAMMPS when you want to use it. So the way that most HPC systems are built is that you don't have access to all the binary or all the versions of all the binaries at the same time. You'll need to ask the system to access them. The way that is done in ARCHER2 is with the module command. So the module command has several options. One of them is the load option, so that you can, yeah, sure, maybe showing instead of telling might be a good idea. Give me a second to share my terminal instead. There we go. Let me know if that the font size is enough or not. So I'm already logged into ARCHER2. So this is the module command. The module command has several options. I believe if you do mashup, you get a list of all the options. To see what is available, seems like the terminal is fighting me today. To see what is available, the module avail command will show you a very extensive list of everything that's available, and it will load on your default pager. So there's a lot of modules available. If you want to narrow that down, you can just type the program you're interested in this case, for example, LAMMPS, and it will show you there are currently 4 installed versions of LAMMPS, which the 29 September 2021 being the default, that would be the D. And if you want to load a module, we do module loads. And if I just do LAMMPS, it will load the default module, which will be the 2022 and September 2021. So if we do module avail again, we should see a L here for loaded. If we want to, for example, I change my mind and I want a different version of LAMMPS, I can do a module swap. And then let's say I want the most recent version of LAMMPS, which is the Feb 23. So I can do a module swap, and that should fix everything in the backend. But if not, the best way to do this is just to exit Archer, log in again, and just load the module you want. Another very useful command is the module spider. Module spider gives you more information than module LAMMPS, and allows you to search with some regular expressions as well if you want or if you need to. And if you select a specific version, I believe it will give you in great detail exactly what's in it, as well as who installed what and what dates and stuff like that. So that's how you load. Keep in mind that you'll need to load these on your submission script when you submit jobs to the compute nodes. There is a way to run jobs interactively, although I don't think we'll go through that today. But the most common way to submit jobs is to create a Slurm script and submit that to the queue. Slurm is the queuing system you use. And then Slurm will, as soon as there's space available, it will submit your job to the compute nodes along with any data that it needs. It will log how many resources you're consuming and keep all of that budgeting in the backend to see if there's enough resources on the project account and everything like that. So just because you have access to 5,000 something nodes doesn't mean that your job will require all of it. And sometimes just throwing more cores at a job does not improve the performance, or at least not linearly. So one of the things that the first exercise I think we'd like you to do is to check how the performance of a program increases with the number of cores, and we'll just be using fractions of a node to see that. The exercise files are in a shared folder. So if you go to TA100/shared, and you should all have access to that, but it's not in work, it's in home. So the exercises from the course are all there. You can copy those to your work directory, otherwise you won't be able to submit any jobs. So let me show you how to do that, for example. So I'm going to change into my work, otherwise I won't be able to submit any jobs. And I've already copied this folder, but let me show you how to do it. So my work folder is now empty. You can copy with the recursive flag, and thanks, Julian. Let me show you that one, then that should work for everyone. So that's work 100 exercises. Okay. So I think Julian missed the Slack share there before exercises, but that should work. So on the first exercise, this is just a simulation that will create a number of ethanol molecules. So just a single liquid, no mixtures, no nothing. And the way to submit jobs into Archer is with a Slurm script. And the Slurm script is the sub.slurm here. And just going through some of these options quickly. So all the Slurm options need to be for any command that you run, and they all start with these #sbatch keywords. So all of these are Slurm commands. Job name is what shows when you're looking at the log of your files, the stuff that you run. Then we have the number of nodes. Time is the time limit that you give the Slurm queuing system to tell it if it goes over this, just kill it. Don't let it continue, waste my budget. This hint no multi-thread is because we won't be using OpenMP shared memory libraries. This distribution block has to do with the NUMA regions. I don't think we'll go into detail over this. If you want to look into this in the detail, I believe we go through this on the ARCHER2 for Developers course. The material is all available online. Tasks per node is how many MPI processes you want the Slurm to create, and CPUs per task is how many cores you want to assign to each task. And then the rest is budgeting keywords. So your account, the A100 is the project we created for this training session. The standard partition is the main larger partition of nodes in ARCHER2. There are others with the high memory ones is a different one. And then I believe there's also reservations for jobs that are scheduled in advance. And then QoS, quality of service, is different settings for different sizes of simulations that you want to run. The short tends to, it has a hard limit of 20 minutes, but that also allows the scheduler to run these short simulations to schedule them a lot quicker than if you request a larger simulation for a day, even if it will only run for a few minutes. The scheduler thinks that you'll have to block X amount of nodes for an entire day, and you might be waiting in the queue a bit longer than if you use the short. All of the partitions and QoSs are in the documentation available online on ARCHER2 docs. So this is when after all the settings for your job are done, you have the actual options for running, in this case, LAMMPS. So we're loading LAMMPS and we're loading the June 2022 version. We are explicitly saying that we're not using OpenMP threads. And then lastly, the srun command is what actually launches a job into the compute nodes. So srun LMP, LMP is the LAMMPS binary. Then we have the -i flag for input file. It's the input.ethanol that is in the same folder as this submit script. Then -l is for the output, the log file. And then we're just using a little bit of bash variable replacement to save the number of processors and the ID of the Slurm job so that there's no overlapping logs. If I run it like this, I am asking for just one core and one task, one core per task. So this will only run in one core. To submit a job to the queue, you use the sbatch command and you append the bash script file to it, and then Slurm will tell you if there's no mistakes in your script. It will give you a job. To check what the status of your job, you can use the sq command. With the --me, it will ask you just for the jobs that have your username. Otherwise, you get a very long list of jobs that you don't really need to parse everyone else's jobs. So the --me is a very handy alias to just show me my jobs instead of everyone else's. So we can see some useful information. We have the job ID that was given to us. We have what partition we're running on, the name of our job, your username, and then ST is the status of the job. In this case, R means running. There's also CG, which when it's canceling or ending, and I believe there's PD for pending, if I'm not mistaken. We can probably see here some other cases. So there's a bunch of R's. There's PD for pending, and then if it's pending, there's always a reason. Be it priority, that means there are other jobs with more priority. Dependency, it's waiting on a job that will write some data that this job needs to continue. These tends to be budgeting problems, so like a budget. QoS mass jobs per user limit has to do with that quality of service. You can't put too many jobs, and all those limits will be on the documentation. Max jobs per user, the same. And if I'm not mistaken, our job should be finishing at some point in the near future. The rest of the information is also useful. The number of nodes that your job is running on and which nodes that is. So in this case, it's just the one node, but in some of the other jobs we saw on the full queue, we saw that some of those lists can get quite large. There we go, our job is finished. So now if I take a look at the log file, you can see what kind of information LAMMPS outputs when you run a job. And we'll go through this a little bit more detail later. For now, and this is what the first exercise will be before we finish this session, we want to look at the wait time, so the total wall time down here, and the performance down here in terms of nanoseconds per day that this simulation would run on this amount of cores. So if you see on the end of the carpentry session file for this session, and I'll paste the table on Etherpad, there is a exercise, and the exercise is to that is not copying right. I'll build up with that in a second. Is to do this with 1, 2, 4, 8, 16, 32, 64, and 128 cores. So maybe if you want to split between you, who does which ones, the ones with less cores will take longer, but it will be less than a minute, then a couple of minutes each anyway. The way you change how many cores is you change these tasks per node variable. So it can go all the way up to 128. And if I submit this one, it should finish very quickly. Julian has pasted the table. Thank you very much. So if you all put your name next to one of the number of cores and start running that job and adding the results to the Etherpad, then we'll take a look at the results and why they might look like that. I'll put the results for the one core in a second. And if you're having any trouble getting the files or running the jobs, let us know and we'll try and help you.
Ruby, how long are we giving them for the exercise?
I think we're due a break soon, aren't we? So I'd say we have like until 11ish should be fine for the exercise, and then we can have a quick break.
Yeah, the break's at 11:30.
Oh, I don't realize I was that quick. I mean, we have more time. That just means if there's any questions, we can go through them in detail.
So I guess give everyone until about 11:05, and then we'll go over the answers.
Yeah, sounds good. So as you can see, just by doubling and doubling again the number of cores that we're using to run this job, our performance is not increasing, by twice each time we double the number of cores. In fact, the performance is getting better, but far and away the ratio is not very good. Now this is a little bit on purpose. The script we're using in this case is not has been selected especially to demonstrate this, but not every type of simulation scales well. So there is a a lot of optimization that can be done, especially with some of the LAMMPS jobs, that might help improve your performance, and just throwing more cores at it is not always the right call. Now, to run certain size of jobs, you will definitely need a large amount of cores or even nodes, because if you have large systems, you'll need if you're thinking thousands of millions of particles, you'll need a large distributed computing system to run it. But you should not forget about improving your script, your LAMMPS code before you actually just submit. And it's always a very good idea to run these kind of very short benchmarking scripts on whatever system you're testing, whatever new system you're going to test, to see what type of scaling it has, and if there's and it allows you also to see how much resources it's going to need to run your simulation for 20 nanoseconds or 100 nanoseconds or however many time units you think you're going to need. It also allows you to take that into consideration. Do I have enough budget for this? Should I maybe look into using a smaller system, or am I okay to wait a little bit more if I use a couple nodes less? It's going to be better on my budget. It will take longer in terms of wall time, but it will be better for my budget. Because as you can see, just by doubling the number of cores, you're definitely not getting double. Now we can make this better. This scaling can be vastly improved with knowing a little bit about simulations and LAMMPS, but you'll never get a 1-for-1 of I double the number of cores, I get the double the performance. I don't think we'll get into a lot of detail today about all of the ways that LAMMPS has to change or improve performance, but all of it is in the LAMMPS manual, which is extremely long but extremely detailed. Some of the things are almost common sense. One of them that will be system dependent has to do with the NUMA codes here in ARCHER2. If you don't want to be running your simulations on a number of cores that is not multiple or a divisor of the number of NUMA cores. So a NUMA region is, I believe, 16 cores. You don't want to be running it on 19 cores or something like that. LAMMPS the performance will probably degrade much more. So the performance will be much lower on probably 19 than it will be on 16, for example, because there will be that overhead of copying memory across the NUMA regions, and we won't be using the other NUMA region. So one of the things that LAMMPS writes to you at the end, just before that total wall time and everything like that, is this handy table of what it spent its time working on. And in this case, we can see that, and I'm going to be looking at a percentage of total here, which is usually what you want to take a look at. So for example, in this example we have here on documentation, you see that it spent 30% calculating the pair interactions between atoms, about 4% calculating the bond interactions, about almost 5% calculating k-space interactions, so long-range interactions, and then almost 60% calculating neighbor lists. So this is a very, very high number, and it really tells you that there might be something wrong here with the way you're handling neighbor lists. So there are ways to reduce the number of times that you recalculate number lists, or increase the size of the list so that you don't have to rebuild it as often, and that can be optimized. And that's usually why you want to run this small size, very quick benchmarking to see what kind of performance you're going to get. And then something that you also want to keep an eye on is this COM communication. That would be communication between MPI processes. In this case, this was run with just the one task, so communication will not be high. But if you have a larger amount, Kevin, I believe angles come at the same as bond. I don't think they make a distinction in this case. So all bond is bonded, not just bonds. So bonds, angles, and dihedrals will come under this bond. So there's bond and long range is the only, or bonded and long range is the only distinction they made, I believe. The pair is the van der Waals, not bonds. Let me see if I can show my terminal again. Let's see if we can take a look at the result of the 128 simulation. There we are. So in this case here, you see that case space was a bit higher. Pair is a lot longer. This just might be the exact script we run on this is not the same as we had on the exercise on the page. But you can see that communication here at least is a bit higher. That's just a communication between all 128 MPI tasks. And if you increase these from 1 node to 2, you will see this communication time increase. Hopefully not massively, but if it starts to dominate the percentage of your communication, then you're just wasting your resources on the processes are waiting for data to be transferred over from a different node. So you're not gaining more. You're not gaining much by increasing the number of nodes on your simulation. So you should be looking into either increasing the performance some other way, or just you'll have to be content with using a smaller amount of nodes, unless your budget is unlimited, and then maybe. Do we have any questions? Because I think I've hit pretty much everything I wanted on this lesson. Julian?
Yeah, I just wanted to also quickly say, I think we mentioned this later in the course, but given that there's going to be a fair amount of time between now and the next session, actually we'll put that to the floor. But one of the really interesting values that's output in this little task timing breakdown is the column right next to percent total, which is percent var ab avg. That's an indication of the load imbalance. So it tells you how much extra work the most overworked processor did compared to the least worked processor. The closer to the closer to like the lower that number is, the better it is. And actually, Rui, if you could show, for instance, did you run on 2 cores?
This, or do you want the
like some low number that you ran on?
I think
not 1, because that's not going to have any load imbalance because there's only 1 core. Yeah, 2 is perfect. But here, if you look at 2, for this specific example, because Rui set it up in such a way that it was going to be massively imbalanced, you can see that the most overworked processor did 250% more work than the least worked processor, which is enormous. Like basically, the reason we were getting the initial slowdown is because the reason that there was no improvement when we were originally increasing the number of cores is because the way that the simulation box was split was in such a way that some of the cores just did no work. And I don't know if you've explained why that was the case, Rui.
I don't think I showed the script. Yeah, no. And since we've not gone through, what the LAMMPS commands are, I don't think there's a lot of value in that yet. We can come back to that maybe later in the session.
But I mean, mainly the main thing to say is that to emphasize the point for this exercise, we ran a simulation where the box is twice the size of the number of particles that's required for that number of particles, which means that half of the simulation box is vacuum. And naively, the way that LAMMPS does domain decomposition, it'll just split the box in half. So when you run on two processors, well, one of the processors has got all of the work to do and the other one has got nothing. But we'll talk more about that next session. So we're meant to hit a break now, and I guess there's two ways that we can do this. So I was going to ask, the course material says that we should be restarting at 12. Now we can either restart at 12 or we can restart in half an hour at 11:45 and then have an earlier lunch. Could you let me know whether you have a preference for which one of those you prefer? You can say it in the chat, or I can ask for hands up. So I guess 11:45. Yep, 11:45 start. Cool, that's two people on 11:45. I'll wait an extra 5 seconds to make sure no one says 12. Great, so let's reconvene it at 11:45. I'll put something up so that people can see that we're coming back at 11:45. Great, well, we shall see you in half an hour. And if you've not done it, I would recommend even launching in the background the additional couple of jobs just to be able to look at the performance data. We'll be looking at it a bit more deeply and a bit more closely later today, but there's a lot of really useful information in that. Cool. See you in 30 minutes.
Just another couple minutes before we start. If anyone has any questions that we can help with before we restart, it would be a good time to ask them. Just raise your hand or type in the chat. So do you mean the table that Julian showed you with how much a CPU was working more than the other one, or do you mean how you'd fix it? Because if you mean how you'd fix it, we haven't talked about it yet. So the table at the bottom of any log of any LAMMPS simulation that you run, there is also an example on the lesson. Give me a second. I will paste a link to the correct episode. So at the bottom of this, there will be an example. In that case, it was run with just one core, so the percent var average will be 0. If I can show you a different one, or you can run using your account, just increase the number of cores, and you will have that column populated. Yeah. I believe that 1,000 atoms per core figure is not going to say ancient, but old. You can definitely do much more than that, but it also really depends on what kind of force fields or fixes you're using. So at least any new system that you're doing, or if you're changing something significant, you should rerun your benchmarks. If all you're doing is maybe changing the proportion of solvent to your target molecule, then maybe the figures won't change too much, so you might not need to worry. If you're trying to do a new ensemble, for example, and it's not going to be just a few thousand time steps. If it's going to be your main focus, then maybe you should test that as well. Does that? Yeah, good. I'm not sure I can give you an answer on what an estimate for atom per core. I think that's really going to depend on exactly what kind of hardware you're running. I think something like ARCHER2, where it's a very modern AMD platform, you might be able to get away with a little bit more than if you're just running it on a laptop, for example. So that's really going to depend. I can tell you that from experience from my kinds of simulations, I've been able to get away with a couple 100,000 simulations on a 64-thread CPU. So that would be what, a little bit over 2-3K. But it was slow. It took a while. It took about, I think it took 2-3 days to do 10 nanoseconds. So it's not exactly, very quickly, but you can get away with it. So if there's questions, for a minimum, that makes sense. Yeah. Otherwise, you're just wasting time waiting for communication.
Yeah, usually when you're thinking about atoms per core, you're thinking about what the lowest number you can have is, assuming that you can always throw more cores at it.
Mm-hmm.
But as long as you're above that minimum, it should scale fine.
Okay, I'm going to share my terminal. Yeah, the first time you run anything large, you want to be sure of what the scaling is going to be, and then of course you start get a feeling into how much changes affect things. But any new system, I would do at least a very small benchmark to see that I'm not too far off. And if it's a new technique, a new ensemble, or anything like that, or a new compute, I would definitely test that just to make sure that, for example, I'm not trying to calculate something too often that's going to slow down the simulation. So some of the computes can really slow down the progression of the molecular dynamics time step. So it can really decrease the performance. So is there anyone that has done no molecular dynamics at all, or should we at least mention what it is? Anyone that has no idea what molecular dynamics is, if you could please raise your hand. Okay, ready. So in a nutshell, molecular dynamics is a way to use classical mechanics to simulate a system of particles. We don't typically care about electrons or electronic clouds or anything like that, although there are ways of doing QMMD, so quantum mechanical calculations in between MD. That is not what we're going to talk about today, just regular old molecular dynamics. So each particle can be an atom, and it's usually the most common case. It can be something that's not exactly representative of an atom, but it's close enough, something like a Lennard-Jones particle, or a particle in LAMMPS simulations can be a coarse-grained group so that's something larger than an atom in a molecule. I've done, for example, coarse-graining of polymers. So in that case, what I was doing is I was taking each CH2 and CH3 group in large polymers and considering them as just one particle. So that reduces the number of particles in the system by an order of 2 or 3. And that can really speed up your simulations, especially because in a lot of cases, the scaling of the MD code can be close to n squared or something like that. Not in all steps, but in some parts. So basically, what you'll have in any MD code is a cycle that goes from a position of particles, then using whatever force field parameters that you've chosen or selected or calculated, you'll calculate the forces in between all of the particles. That with those forces, the acceleration for each particle is calculated using that, and the size of the time step in time units. Then you calculate how much a particle will move between the time step now and the next time step. And then with the new positions, the cycle starts all over again. You then recalculate the forces, recalculate accelerations, calculate the new positions, etc., for how many time steps you selected to run your simulation at. I'm not on anything yet. I was just talking. That cycle is on the top of the setting up simulation in LAMMPS exercise, but I was just going to start with the input file next. So that was it. There is a pictographical representation of that on the episode. I can paste you the link. There you go. So to tell LAMMPS exactly what to run, how to run it, and including several choices of how LAMMPS should be doing things, you need to provide LAMMPS with an input script. An input script is comprised of various LAMMPS commands. All of LAMMPS commands are available for and documented in the LAMMPS online manual, which is, like I said before, very extensive, but also very well written and has all the details that you will need. And typically, not every command is dependent on where it's positioned, but some of them have to come before others. So you'll have to define your units, for example, that we'll see here in the bottom of the file. There's things that you need to define before you tell the simulation to start, for example. So there's no hard order for all of the commands, but some of them need to come before others. I believe there is a large section of the LAMMPS manual that goes through some of that, but in general, your general setup should come before the setup for your next simulation run. And the last thing you have is the command that tells LAMMPS, now run it for X amount of time steps. So this file is for Lennard-Jones fluid. And here at the top, we're creating just a variable that will set the density that we can change later on the exercise. The first command, proper command here you have is a units command. Happens, LAMMPS, have a lot of unit types. There's metal, there's real, there's, I believe, lattice or something like that. I tend to just use real myself. I believe Julian uses Lennard-Jones a lot more. These define the units of both inputs and outputs of LAMMPS. So things like distances, time steps, stuff like that. In this case, with LJ, it's going to be all LJ units. So time is not in seconds, it's just LJ time steps is basically a unitless system. If you use something like real, the time step would be in femtoseconds, the distances would be in angstrom, energies, I believe, would be in kilocalorie per mole. All of that is in the LAMMPS manual, which maybe is a good idea for me to show right now. Let me change my screen. So if you follow here the link on the episode, it will bring you to the LAMMPS online manual, directly to the units page. And pretty much all of the manual pages have the same structure. You'll have first a box with the the command syntax and then an explanation of what argument which can be, and then examples and descriptions, and sometimes even some like actual theory and equations, if that's the case, and even citations to scientific papers explaining how or why things are done. So for example, here, it will give you for each style, so LJ first and real, what each unit will be represented at. So here, as you can see, LJ is all going to be dimensionless things. In real, you have stuff that makes more sense for maybe soft matter physicists and even stuff like that. So for example, distance in angstrom, like I said, temperature in Kelvin. There are other units, SI. I should have remembered that one. Not that many people use it. I think metal is probably the most used after real. But all of the LAMMPS manual will have the descriptions for every option like that. You might want to take care in some cases that you're looking at the correct version of LAMMPS. So in this case here, at the bottom, we're looking at the 8th Feb of 2023. Our version that we're running is slightly before that. So there might be some discrepancy between what the manual says and what you're actually doing, but usually they will have a note saying that it was introduced in version X or version Y or something like that. I don't believe that LAMMPS keeps the older versions of the manual available. You might be able to download it from GitHub. I'm not 100% sure. So back to our input script into creating something that will run. So after selecting what type of unit, we are selecting our atom style, and our atom style just defines what type of properties each atom object will have by default. Atomic, I believe, is the basic that stores coordinates, velocities, atoms ID, and atom types. Every other atom style will add some other properties that might be useful for whatever kind of simulation you're doing. Can two types of units be used in one simulation? I don't believe so. I believe you would need to convert the units into force field parameters, so that should be trivial to do, and then you can use the output in whatever form you want. So after atom time dimensions, LAMMPS is able to do 3-dimensional or 2-dimensional simulations. It will not do 1-dimensional or more than 3-dimensional simulations. Not that many physical systems would fit more than 3 dimensions anyway. And then after that, we have boundary conditions. So boundary conditions are a way in molecular dynamics to reduce the size of the system to something that can be smaller but repeatable. Something in this case, if we want to simulate infinite fluid or the bulk of an infinite fluid, what we can do is select a section in the center and then repeat our unit cell many times around it. And the way that periodic boundary conditions, which is what these 3p on each direction mean, so in the X and the Y and the Z direction, what those mean is that should an atom move from, should an atom exit our box on the right side, it will come back in on the left side. So that is just a way to keep the number of atoms consistent in a unit cell, but also to keep a not effectively, but theoretically infinite number of atoms while simulating only a small subsection of that. There's a lot of physical theory behind this that I'm not going to go through right now. The way that LAMMPS calculates this is using the minimum image convention. That means that each atom will only see the closest version or the closest image of every atom. I'll show you what I mean using the episode. So imagine this atom here on the left side, the blue atom on the left side of the box. Oh, that is a great question. Is the coordinate system necessarily Cartesian? For coordinates, I believe so. At least I've never seen anything other than Cartesian. But I could be proven wrong. You might want to double check on the LAMMPS manual, but I believe it will be Cartesian. If Julian could have a look. So like I was saying, maybe this top here is a better example. So this top right blue atom here, it will see this image of that atom, which is basically the same. So this box is just copied many times over. You will see this one because it's closer than that one, even though they don't share a periodic box. So basically, the way LAMMPS implements it is that each lamp will see the closest, in terms of three-dimensional distance, the closest version of any atom. And that way, it avoids any kind of self-interaction shenanigans, as long as you make sure that any of your bonded systems, be it polymers or smaller molecules or anything, as long as they don't span more than half the box length, you will be fine. Other options here for the boundary command is fixed, and that just means that you're not creating all of these periodic images. That can be useful, for example, if you're simulating a surface, for example. In one of the directions, you might not want to repeat the images because you have what is compared to an infinite surface, for example. I've done some of that, for example, with lubricants next to an engine surface. And so in one of the directions, we had an iron oxide layer, and that was effectively infinite. So we wouldn't want to repeat those. Then we have the lattice command. This lattice command will define in this Lennard-Jones simulation a 3D lattice with the density that we define with the variable above. So this would be equivalent to saying lattice SC 0.8, for example. So this is the same, it's just we're using a variable substitution here because we defined the variable up there. All of the spacing in between words here doesn't really matter. By the way, white space doesn't really matter in LAMMPS. It's just a way to keep things separated and to separate basically the command word from the arguments, so it's easier to read. The region command, this tells, in conjunction with the lattice command, this creates a region in space between x minimum, x maximum, y minimum, y maximum, z minimum, and z maximum. So in this case, from 0 to 10 in all directions, with the density that we defined above. This defines a region in space with lattice points that then we can create our box and our atoms on. So basically what we're doing is with that 0.8 density, we're creating a box of side 10 and populating it with atoms. So this is the easiest use case, the easiest way of creating a LAMMPS. It works well for Lennard-Jones fluids. If you have something more complex with different kinds of molecules, you might want to use a different approach. But this one, as a first exercise, as a first approach, works very well. Next, you need to define your force field parameters. In this case, first one we're going to do is a peristyle. We're going to be using a Lennard-Jones with a cutoff at 3.5 sigma units. The cutoff here is because these Lennard-Jones potentials tend to 0 but never actually reach 0. So these here are just saying that at 3.5, the value is so close to 0 that it might as well be. And then in conjunction with the next keyword, pair modify, we're just saying that whatever the value was at 3.5, that's now 0. So shift the entire potential curve to up, so that at 3.5 it crosses 0. Do not care about the potential after 3.5 distance units, and we'll just care about these non-bonded interactions under 3.5. And then we're setting the coefficients. The first number is the atom type of atom A and the atom type of atom B. In this case, we just created one type of atoms. They're all going to be the same, but simulations can have many, many more types of atoms. And in this case, we're just setting our coefficients to be 1 in both the distance and the energy depth. What are these distance and energy depths? Let me show you what a Lennard-Jones potential looks like. Share screen. No. So here we have a Lennard-Jones potential. This is a potential well with a minimum at here. I think it's going to be 1.1 something in terms of distance, and we have a depth of 1 here from 0 to 1. So is the cutoff value in sigmas or angstroms in real units? So in real units, it will be in angstrom. So the cutoff will be in whatever distance units the unit command that you use set it to. So here in Lennard-Jones, it will be sigmas. If your units command is real, it will be angstrom. If it's any of the other ones, it will be whatever distance units they use there. So if you use SI, it will be meters probably. So you will have to change those accordingly. Right. So these Lennard-Jones potentials are one of the simplest ones. There are many, many, many others. Which one you use will depend heavily on what application you're looking into and what kind of things you're studying. And that's not really part of today's workshop. But if you look at the LAMMPS manual, and once again, link, there are many, 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 many of them. There is a very, very large long list of all of the types of pair styles that you can use on your simulations. And for that, you'll need to have a little bit of more scientific physical knowledge of what you're trying to study. Right. So the last thing you need to set up after the pair coefficients will be the mass of your particle, because without a mass, you can't have an acceleration. There we go. So that's the last thing. Once again, you're setting the masses of particles of type 1 to 1.0 in whatever units. And in Lennard-Jones units, it's just 1 to make things simple. Physicists like simple things. The next thing, and one of the things that can influence the performance of your simulation, are neighbor lists. Neighbor lists are a way of limiting how many pairs of atoms that LAMMPS needs to check to see interactions. So I think, so since we're cutting off our interaction at 3.5 sigmas, it doesn't really make sense to be calculating the interaction between particles that are more than 4 or 5 sigmas away. So if we trade off a little bit of memory, so to keep these neighbor lists, we can increase our performance by having to check less pairs of atoms. So with these neighbor lists, what LAMMPS will do is for each particle, it will calculate a list of other atoms in the vicinity that are close enough that they might affect the forces. So it does that by taking into account your peristyle cutoff, if there's one, with an extra buffer. I believe they call it the skin distance, which is this 0.3 here in the neighbor. So that means that a neighbor list for each atom will be every atom within a distance of 3.8 unit distances, sigmas, of each other. These neighbor lists are not typically recalculated every time step, and one of the maybe simpler is not the right way, but one of the easiest ways to improve your performance is to change how often you're recalculating these neighbor lists. The trap here is that if you're not updating their neighbor lists often enough that a new particle can come into your cutoff distances but wasn't caught in the neighbor lists, then your interactions will be wrong, just basically wrong, not just slightly off, they will be wrong. There are not easy ways, but there are ways to calculate how often you should calculate these neighbor lists. LAMMPS at the end of the log will also show you how often they were recalculated and how many dangerous builds there were. I believe dangerous builds is something that moved more than half your skin distance, so in this case, more than 0.15. And also the, I'm going to show that. There we go. So the diagram to show your Lennard-Jones cutoff is this, and then you have an extra buffer, the skin distance, that every particle that's included under that. In this case, what LAMMPS considers the particle is the center of mass of the particle. So particles in LAMMPS are considered point particles. Whatever interactions happen at distances aren't really hard spheres or anything like that. It all has to do with whatever potential you chose. The center of mass of the particle, or the point particle, basically is what LAMMPS considers for any of those distance calculations. So it's not radius to radius or anything like that. Yeah, so recalculation, that will be the name modify command. That with that you can change how often you recalculate your neighbor lists. The first part, the late n, means after we just rebuild our list, wait at least 10 time steps before you even check it. So trust that in 10 time steps there will be no new particles to take care of that. And then the everyone means that after that 10 time step, every time step, if any particle is moved more than that skin distance, then we rebuild our neighbor list. How often you rebuild or you check is a bit of a trade-off because checking it also takes a little bit of overheads. And also the faster your particles move, the more often you will have to rebuild your neighbor lists. That is just something that can't be avoided. But if you're simulating something at lower temperatures or something that's more viscous, you might be able to get away with rebuilding your neighbor lists a lot less often. And that will give you, in trade-off, more performance. You will use a little bit more memory. So for example, if you want to increase your neighbor list, you have to rebuild your neighbor list less often. The rebuild will take a bit longer because every atom will have more neighbors, and you'll need a little bit more memory. So it's not always just make the neighbor list infinite. It's not really a good trade-off either. So after some kind of general setup, we can then start telling LAMMPS the initial conditions of our simulation. So in this case, the first line, the fixed linear momentum, is going to zero all the momentum in all particles in all directions, just to make sure that there's no spots of very high momentum that might disrupt our initial status. That can happen, and that can make your simulation crash very quickly. So if it's less common in these lattice cases, but if you're packing random molecules, if two molecules are too close together, your initial forces will be too high, and then one of them will be applied a force so large that will move so much in a couple time steps that it will exit the periodic boundary conditions before it's tracked, and it will crash your simulation, saying something like processor X bound atoms missing or something like that. So zeroing all your momentum, or in other cases, minimizing the energy, for example, is a very good way of making sure that your systems aren't too energetic to start. And then the next fix line, we have fix one. This one is just a name for this fix that we can then reference in other commands. It could just be something like NVT, for example. It's just a name, can be numeric, can be alphanumeric, can be whatever. And then we're applying that to all of the particles. There's also ways in LAMMPS to just group some of the particles in different named groups so that you can apply different fixes to different groups. That's a bit more advanced techniques. And then you're telling LAMMPS that you want to do an NVT simulation. NVT here is one of the ensembles. It stands for constant N number of particles, V for volume, and T for temperature. So you want a constant number of particles, constant volume, and constant temperature. That means that your pressure will vary. There are many other ensembles that you can use. Maybe the most common in my line of work were NVE as well. So to keep energy constant rather than temperature, and another one would be NPT. So we could keep the temperature, the pressure constant rather than the volume. And in that case, the simulation box changes size, but the pressure is kept at a defined pressure. And here we're telling it that for the temperature, we want at the start of the simulation what temperature to be 1, at the end of the simulation, and by simulation I do mean the next section of the simulation. So LAMMPS can do several sections in a row. This sets it for the next section of the simulation. That's defined by the run command that we'll check later. And then the last argument here is called T-damp, or temperature damping. This is in time units, and this is basically how long does the simulation wait to enforce an increase or a decrease in the temperature, to see if small fluctuations are fine around 1.0, but if in 5 time units in a row the temperature keeps increasing, then the thermostat will start acting and starting removing some energy from the system or adding some energy into the system if that indeed is the needed case. Around 100 time steps is usually the suggestion that LAMMPS gives. Just keep in mind that the T-damp here is in time units, so there's a bit of a disconnect between the time steps and the time units. So the time units is the 1 Lennard-Jones time unit. The time step, I believe, we're going to be defined here is much less than 1. So just keep that in mind. And then lastly, we're introducing what is an effective way of choosing damping. Like I said, except in very particular cases, if you choose something around 100 time steps, you should be fine. unless you're really increasing your temperature such high, for example, that a spike might mean that you're ejecting particles, and then you might want to tighten that up a little bit. In general, you shouldn't see, or in most general cases, you shouldn't see an effect of changing TDAMP too much. At least not in the studies, the systems I've studied. Julian, you've had a lot more experience with Lennard-Jones. Are they more susceptible to the TDAMP?
I've not really played around with TDAMP. I mean, in this case, we're definitely nowhere near the 100 point because we're doing it every 5 time steps, right? Because the time unit's 1 time step.
No, it's 5 time units, not 5 time steps.
Yeah, but in Lennard-Jones, they're the same thing, aren't they?
No, your time step down below is way less than 1 time unit.
Okay, cool. Oh, yeah, so it is. Yeah. And should this work for a Langevin thermostat? Yeah, the Langevin definitely has a damping parameter. But the way that the Langevin damping parameter works is it sort of like simulates an almost fluid-like in which you've got your sphere, and that sort of slows down how quickly or how slowly your sphere can gain or lose temperature.
Cool. All right, so finally, we're almost ready to start the Lennard-Jones simulation. All we need is some initial velocity on our particles. So again, velocity command with some parameters. This all is again what particles we're applying it to. All just means the group that contains all the particles. And then we are creating new velocity. There's also ways to modify it, being it decrease it for some people or for some particles, or adding it to some particles, something like that. Then the temperature, we're using temperature of 1 Lennard-Jones units up here, so we're using the same here. And then the next number is just a random seed number. Just you can use whatever. If you use the same with the same system, you should have the same initial velocities. And then the last thing is MOM no. That means momentum no. So do not add momentum to our particles. They start with some velocity, but it also linears. Sorry, it's the total momentum not for each particle. The total momentum of the system is 0. So that makes sure that there's no, if you're simulating a fluid, that there's no, flow in from one side to the other of the box, for example. Then the time step. So this is 0.005 Lennard-Jones units is what each time step is going to be, and then the thermostat command tells you what details to put in that log file that we had a look at. Not so the beginning will always be the same. The ending table will be the same. This is the what shows in the middle. So if I can, so here in the middle, so that thermostat command defines what happens from here on onwards. So these step, CPU, temperature, total energy, pair energy, longer range energy, van der Waals, volume, length of the X side, and pressure. So this is what was selected in this case. I believe that in the Lennard-Jones case is slightly different. We have, step, temperature, total energy, potential energy, kinetic energy, pressure, volume, and density. All of those and more, many more things are described in a manual. You can take a look. You can also output here some of the things that you can make LAMMPS calculate for you, being it, for example, the volume of only part of the box, or the temperature of a subgroup of particles, or the velocity of a subgroup of particles, or something like that. By default, all of these commands calculate the properties for the entire box. So in the volume and density, for example, but you could calculate a subsection if you define those calculations yourself. And then the next command, the thermo, tells LAMMPS how often to write these details. So in this case, we're going to write every 500 time steps. There's going to be a line on the log file with all of these details. One of the that's a good example. One of the things that you can calculate, for example, and they're usually denoted by these compute commands. This is a RDF, radial distribution function. I think we'll go into detail of what these means and how to create or read them this afternoon. But these two commands will also calculate this and write the result in this file. I'm going to comment this out. We're going to take a look at that this afternoon and then explain in detail at that point. And finally, the run style just chooses in this case, the Verlet algorithm. I believe that the default would be the velocity Verlet. And then finally, we're telling LAMMPS to run this simulation that we've set up for 50,000 time steps, not time units. It's an important distinction sometimes that LAMMPS uses both in different commands, and if you mix them up, you'll get some interesting results. So this will run this system that we created, Lennard-Jones particle with density of 0.8 with 10 units on each side for 50,000 time steps with a time step of 0.05. It will output all of those things that we set up here every 500 time steps to the log. It will use all the pair style that we set up and the mass and everything like that. And here we could, if we wanted, for example, now change. At this point, we could tell LAMMPS to change the time step, for example, or change the ensemble that we're using, and then run again. And then at this point, you could do another run, 50,000 or whatever, and LAMMPS would continue the run from where it was with the new changes that you've made. So that is a way of chaining steps of your simulation together. But you can also just write the state that you were at the end of this simulation, and then start analyze your data, see if it's all is going well, and then start from that point with a new script, basically. So, for example, if you want to continue from this, you could write a restart, then give it a file, and this creates a binary file with all the information of your system. There's other ways of doing this to create text readable formats and stuff like that. I believe we'll go through this later in this afternoon. But for now, let's take a look at what it would look like. So I believe the exercise for this session is a very simple one, is that are you still able to run a LAMMPS job in ARCHER2? Do you remember what the command was? Hands up, anyone? No volunteers. How would you launch this job on ARCHER2? Exactly, Mark. Spatch, it's our most used command ever, I'm sure. And if I did make any mistake on my sub slurm, which is not impossible, let me see, looks good. Should have. There we go. That's done. and it took 4 seconds to write a small job. So here you can see, as comparison with the previous job we were running. So because the other one was using real units, this one is using Lennard-Jones units. You see that the performance here is not nanoseconds or whatever, is given in tau per day. So that makes sense. And we can see here that this script, it's much more balanced in terms of the division of labor between CPUs. We're spending a lot of time in communication, so that tells us that probably we don't have enough atoms to be worth running on one entire node. So if we reduce the number of cores in this submission slur, we probably wouldn't see a lot of reduction in terms of performance, and it would be much cheaper on our budgets. So we will analyze the output of this file, I believe, on the next episode, next session. For now, I'm happy to answer any questions you have.
Actually, as well, I've got an extra quick question for everyone attending. Please could you let us know, are we going a bit too quickly over this? Are we going a bit too slowly? Would you like anything, if you let us know, like if there's any bits that you'd like us to focus a bit more on, we're more than happy to do that after the lunch break. But yeah, if you could let us know whether we're going at around the right speed or too fast or too slow, that would be helpful.
That is a loaded question because that really depends on what kind of structure you are interested in. If it's something with a very precise placement, you might have to look into something like PACMOL, or what is the Python one? Is it? It's not MD-Trash, I believe. It's MD-Trash. It is not. I will come back to you with the name of that because I'm forgetting now. Otherwise, if you want a very precise starting position of your particles, then you might want to look into something like that. If you just want random placements, LAMMPS is, as of the last couple of years, able to do that for you. You can see an example on the input file of the first exercise. We do basically that. There is we have a data file with the properties of one ethanol molecule, and that is then repeated a bunch of times in the input file to create a fluid box that is quite large. To reuse a restart file, so you can, instead of defining all of the properties of your molecule or atoms or particles, you can just read _restart. However, be very careful of what is written on the restart and what is not. So if you can check, oh, that's good. Julian, do we cover exactly what the restart file contains and what it doesn't?
Yep. We cover exactly the properties that are contained in it. We cover the sorts of things that you need to define, the things that you need to redefine, and we also cover how you can use a data file to do very similar things.
Okay, so where are the long-range interactions specified for ethanol? So on the ethanol input file, if you see here, you see the k-space. So that would be your long-range non-bonding for Coulombic interactions. Here you define what type of, how they are calculated. So there's PPPM, so particle mesh method. There's the Ewald mesh method as well. And then the charges of the atoms, which is what would get you the forces between the interactions, are set here on the set charge command. There are there are many ways of doing this. LAMMPS has over the years tried to be able to be compatible with other software that generates inputs and stuff like that. So there is a way that you just give it all the atoms with the charge already, or you can set a charge for the entire atom type. There's plenty of examples both in this in our input files and in the LAMMPS manual. So the ethanol one also has, so this is the data file that contains just the one molecule. So as you can see here, there's 9 atoms for ethanol with their coordinates. And then we have the atom types for each atom, and then a list of the bonds, angles, and dihedrals for all of them. So this is one of the way to use this, just the information for one molecule, and then you can multiply it in your input file when we do stuff like this. We create a lattice and then a box. It's a bit more convoluted, but it allows the flexibility of quickly, just by changing this parameter here, for example, we can change the size of the simulation. It's a bit more complex, but at least we want to give you this to give you like an example of what kinds of things you can do, and then you can analyze these and whatever commands you don't understand or don't know, you can search the LAMMPS manual and read how to use them. Any more questions? So PACMOL is a bit outside the scope of today. If we have some time at the end, I'll be able to show you because I've used it so much. PACMOL is quite easy insofar as there's only maybe a dozen or so commands that you can take and use. You might need to then use something like VMD to because PACMOL will create an XYZ file, so just a plain coordinates with no other bond or dihedral or angle information. So you might need to use something like VMD to then create that topological information for you. So that might be a bit more convoluted. But if there's some time at the end, I can show you, or if not, you can email me. My email's on the course, and I can send you some information on how to do that. Maybe something important, has everybody been able to run at least any of these simulations on ARCHER2? If anyone still has having trouble either logging in or running the simulation, please let us know. We can fix it or help you fix it. So what interactions are included by default? Do you need to compile again to add additional interactions? That is a great question. That's going to take a couple of parts to reply to. So if you mean what interactions LAMMPS can calculate, it can calculate pretty much anything that's been implemented, and if it's not implemented, it can be added, but that will need some C++ code. By default, I believe we can check what parts of LAMMPS. So LAMMPS is divided into different packages. We're using the June. There we go. So if you do, I never remember if it's help or version of something. There you go, -h, because -help would be too easy. So if you do LMP-H somewhere down here, it will tell you exactly what capabilities this exact version of LAMMPS has, both in atom styles, more importantly in pair styles. Of that huge list that I showed you earlier, it's possible that not all of them are available in this exact version. If it is not, you can compile your own version of LAMMPS on ARCHER2 with whatever packages you need. And we have, I wouldn't say extremely detailed instructions, but there are instructions on how to do that. I'll grab a link. So these are the instructions that we use to build the most up-to-date version of, or this version of LAMMPS we're using, the June 2022. So those instructions should work with whatever, if you want to compile your own version of LAMMPS, and you can just change the package options at the end to suit your own needs. Then instead of loading the LAMMPS module, you just have to point the srun command to whatever compiled binary you compiled yourself. So that's perfectly fine. There's people doing that in ARCHER2 all the time. If you mean, and maybe this is not the question you asked, but if you mean like the bond angle dihedral interactions, so as long as you define those, LAMMPS will calculate them if your pair style supports them, I guess, is the caveat. Was any of that what you asked, or am I way off the mark?
If I can interject real quick as well, I think usually the best way to know whether or not you can run something is if you look at the LAMMPS manual. Let's say you want to run some LAMMPS pair style. You can look at the LAMMPS manual, and at the bottom it tells you what the prerequisites for it are. And provided you know which packages you compiled your version of LAMMPS with, then you can tell whether or not you need to recompile.
I can show one page as an example. Give me a sec. There we go. So this quip pair style command is one that is part of a specific package. So if you go down here to the bottom in restrictions, it says this pair style is part of the ml-quip package, which is not one that we install by default. So if you want to use something like this, you will have to build to compile your own version of LAMMPS with this one with this package activated. If you want to do this and you're having any trouble following the build instructions or anything like that, you can always email ARCHER2 support to have someone from the CSE team, like myself or Julian, to help you through this and point you to all the documentation that we have, or if there's any documentation needed, we can create that as well. Well, I think this session has been going for an hour, so I'd say we can maybe break for lunch.
Yeah, that sounds like a good idea. Same question as before. We're running about 15 minutes early. Would you rather we return from lunch at 1/4 to the hour, so in an hour exactly, or would you like a slightly longer lunch of 1 hour and 15 minutes, and we'll return at 2 p.m. UK time? So one of the questions is, are we going to be doing any granular examples? I don't think we've got any ready, unfortunately. So sorry, no, probably not today. I might be able to dig some up, but I've not really touched them in years. So regarding timing, cool. Well, in that case, I suggest we reconvene at 2 p.m. if everyone's okay with that, rather than 1:45, just in case there are people who have meetings that they've planned over the hour gap or anything like that. So I guess we will see you all at 2 p.m. Hope you all have a nice lunch, and see you then.
Yeah, and if there's any questions, you might leave them in a chat. We'll be around to either answer them, or we can answer them on the next session when we restart.